All right, should be recording now. Okay, so like I said, today we're going to be kind of starting at the fundamentals of MRI. Because this is over Zoom, I want to do my best to make everything interactive and more like a discussion when possible. This first session won't have as much of that as I would like. It's mostly going to be talking and showing animations when I can, just because the actual there's not that much to discuss if you don't know what I'm talking about. It's kind of, it feels like I'm just kind of leaving you like hanging out there to dry to answer these kind of questions. And if you do know what you're talking about, then it's basically the same as me just kind of like walking everybody through it together. So I just want to get everyone on the same page. And then later sessions, I hope will have more of an engaging format. But I might still stop and ask some questions when possible throughout the session. So be on your toes, I guess. Today, I'm hoping to get through about like 10 different slides of diagrams. You can see the outline here, starting with kind of like the basics of the hydrogen atom, which is what we're looking at in MRI. And then getting all the way up to basically everything we need to understand for what kind of stuff we're actually collecting with MRI. And then in later sessions, we'll get into, how do we take this information and make an image, and then build off of that and talk about different types of images like structural and functional and all that kind of stuff. But in order for everyone to understand the later stuff, we need to kind of start with these fundamentals. So that's the plan. So let's just jump right into the hydrogen atom. In MRI, there are many different particles we can look at, but conventionally, we are looking at the hydrogen atom, which has a very complicated and technical diagram. So I'm going to do my best to draw it. It's a circle. That's because the hydrogen atom, it has an atomic number of 1. That means it has 1 proton, and it has an atomic weight of 1 usually, which means it has no neutrons. It just has 1 proton, right? So the hydrogen atom here can also just be called a proton, or sometimes in MRI it's called a spin, which we'll get into a little bit later. And essentially the important property of this atom or this nucleus is that it has a positive charge, and it's always in motion, right? Every bit of matter in the universe is at like motion at the very minuscule level. So this proton that I've drawn here is always wiggling back and forth. It's spinning with some sort of rotational frequency or angular frequency, and that generates a magnetic field because it has a charge, a positive charge. Anything with a positive charge, it will generate a magnetic field, whether big or small. That's how the Earth has one as well. And that can be represented with just kind of like field lines. If you're not too familiar with field lines or what magnetic fields look like, don't worry, it doesn't really matter that much. I'm just going to draw some on here to represent that this thing is generating a magnetic field. So say I'm going to draw one with an orientation that's slightly oblique. We'll just have like a tangential one, and same thing on the other side. Very technical drawings to start. So this magnetic field has an orientation, which you can kind of see from the angle that I've drawn it at. I'm just going to represent it with a red arrow here. And yeah, that'll be useful later, as understanding the orientation of this magnetic field is important for MRI. But the important other the other properties of the hydrogen atom, it's got that positive charge, it's constantly moving, which is generating a magnetic field, and it has this property that's just an intrinsic property of any particle, like a proton, called nuclear spin. So I'll just write that down here. Nuclear spin. This is just a property of a particle, like I said. For hydrogen, the number that is associated with its nuclear spin is 1/2. It's just because it has 1 proton and no neutrons, which means it has an odd number of those particles, it has 1, so its spin is 1/2. There's probably a more correct way to describe that, but I've never run into needing to know it for an exam, which again is kind of like the level that I'm teaching at. So we're leaving it at that. It has a spin of 1/2. It's not the only particle with a spin of 1/2, but it does have that property. Other reasons to look at hydrogen in the body are there's a lot of hydrogen in the body, right? There's 2 hydrogen atoms for every water molecule in our bodies, and we are made of a lot of water. That means I heard once that if you have like a sugar cube of hydrogen atoms or water, what have you, there's about like 10 million hydrogen atoms in there. So there's a lot in a small volume. That means if we use MRI to influence hydrogen, we're influencing a lot of matter in the body, which is good in terms of how much signal we can record, which will come up again and again. Not so much today, though. Okay, so that's basically the outline of the hydrogen atom, and then we'll jump into what happens with once it's in an MRI scanner. Okay, just apparently I didn't leave enough room here. I think I can change that though, or I can just deal. All right, cool. Scroll back. Okay, so in the body, we have many hydrogen atoms, as I just mentioned, which means at equilibrium or at rest outside of a magnetic field, we can represent that as just many different circles. I'm just going to draw 6 here, and each of those is generating its own little magnetic field with its own orientation. So I'm going to represent those with the arrow that's denoting that magnetic field's main orientation. And they're just randomly distributed because why wouldn't they be? They're just doing their own thing. There's no external force that's causing these magnetic fields to do anything fancy. So there's just a bunch of hydrogen atoms, and the net result of this little collection of many hydrogen atoms is no magnetization, right? And if that doesn't quite make sense intuitively, the concept here is just that, you know, if all of these hydrogen atoms were pointed in the same direction, then their magnetic fields might add up and cause there to be kind of like a larger magnetic field that could influence other tissue or other objects. But because these magnetic fields are oriented randomly, they all cancel each other out, essentially, like these 2 that I happen to draw in exact opposite orientations. If you add those 2 magnetic fields together, they cancel each other out, so there's nothing there. Oh, actually, it looks like I drew them all fairly opposite, so nailed it. But if we put these in a MRI scanner, we're putting them in a very strong magnetic field, which I'm going to represent with a dark green if I've got one. And we usually refer to this as the B0 magnetic field, right? That's just a notation. B, for some reason, represents a magnetic field. At least that's how I learned it in engineering, and that seems to hold up when I was learning MRI physics. And B0 or B0 is just like the main magnetic field. We'll talk about B1 a little bit later, and those are the only 2 you really need to care about. And when you have these hydrogen atoms in a magnetic field, I'm just going to put in B0, the individual magnetic fields of hydrogen atoms are influenced by the strong magnetic field, and they tend to align either with or against the magnetic field. So I'll draw these 6 hydrogen atoms again in slightly more geometric alignment. And now their orientations tend to be either angled upwards or they can be angled downwards. I'm going to make this one drawn similar that way. They can also be oriented downwards. So still like primarily vertical orientation for these magnetic fields, but they can be up or down. As a rule of thumb, I initially learned that these magnetic fields can only be in one of 2 states, either oriented up or down, and that really simplifies things. You can definitely think of it that way, and it causes you no problems at all. It gets a little bit more confusing if you read further, as I made the mistake of doing a couple times, as to what is actually going on with each individual particle or spin. The secret reality is that there are still hydrogen atoms in all orientations, like we have on the left here, but they're still randomly distributed, canceling each other out, except for this excess of spins that are oriented up or down. So we really only care about those ones. So that's a little nugget of secret wisdom if you want to remember that. But if that's a little bit too high level, just remember that hydrogen atoms in the B0 field tend to be oriented up or down. There's another important feature of spins that comes in now, which is precession. If you haven't heard this word before, that's okay. It's just like a wobbling top. I'm going to bring up an animation now. And this looked okay when I was testing stuff out, so hopefully it looks okay now too. This is what precession looks like with the example of a top. So once it starts wobbling, then it'll precess on some off axis. It's no longer up and down like it started. It's still, oriented vertically, but it's also wobbling around on an off-axis orientation. That's kind of like cycling around that vertical, axis that it was initially on, right? So the same thing happens in MRI, and all of these atoms are going to be precessing in the same direction for the most part, I think. It might be different depending on whether they're up or down. Thankfully, that doesn't really matter for our purposes. I think they are, though. The ones that are oriented in the up direction, but these blue arrows are rotating, I guess, in the clockwise direction. As you can see with my crudely gesticulating pen here. The ones in the downward direction would still be clockwise. All right, great. If you're wondering why I'm pausing, it's because this direction is determined by a thing called the right-hand rule, which is a weird thing that always came up in engineering. Essentially, if you have a magnetic field as represented by your thumb, and then you have another magnetic field that's represented by your other fingers, there's a force applied in the direction that your hand rotates. So you can kind of use that as a rule of thumb to figure out which direction things are going to be precessing. It doesn't really matter, though. All we need to know is that these hydrogen atoms are wobbling, and they are rotating in a cyclical fashion. There's a couple other things to touch on here. And if I'm going too fast, please let me know. We don't have to get through everything today. In fact, we likely won't. So we can slow down whenever you like. Just interrupt me or post a question if you'd rather not. Okay, so there's two important factors to talk about now. First is there is now a net magnetization of this group of hydrogen atoms. And that net magnetization is oriented upwards. So I'll draw that as a little arrow over here, say net magnetization. And let me go into why that is the case. So if we think of these magnetic fields as separate vectors, which is just that arrow with an orientation and it's rotating like we've been talking about, there are in this image there are 4 hydrogen atoms that have their magnetic fields oriented upwards. Just draw that in green, a lighter green though. Lost my arrowhead. All right, so there's 1, 2, 3, 4 hydrogen atoms that are oriented upwards, right? Generally, they're off axis. But if we think about just their vertical component of that magnetic field, it's upwards. Whereas there are, let's go in purple here. There are 1, 2 spins that are oriented downwards, right? Again, off axis, but we're only worried about their vertical orientation. So if we're just doing like vector addition, adding those magnetic fields together, these ones are going to cancel out those ones, which leaves us with 2 spins that are oriented upwards that aren't canceled out. And that's contributing to this net magnetization field oriented with the B0 field oriented upwards. And we also need to think about the lateral component. So if we have my arm, actually I'll draw it because my arm is not that useful. If if we have a general, a vector like this, it can be split into vertical components, which I guess I'll make blue, which the vertical component for this arrow that I've drawn would be like that. So it has some orientation and some magnitude, as every vector does. And then there's also a lateral transverse component, which would be broken down like this, right? So if I had an arrow oriented the other direction, it would have the same blue component vector, but then its lateral or transverse component would be oriented the other direction, right? And that's essentially what's causing there to be no net magnetization in the transverse orientation, because these hydrogen atoms here are still oriented randomly in the kind of the transverse direction. They're processing at the same rate, which we'll touch on next, but they're oriented in different directions laterally. They still cancel each other out. So let me just draw another mini diagram here. So this is a top-down view of the above. I'm just going to draw these spins as points instead of circles. And now all of the vertical vertical components are oriented kind of like out of the screen or into the screen. So you can't really see them here, but we can see those transverse components, which I'll label here while I'm thinking about it. And I'll draw them in green, and maybe this one is oriented that way, and this one's that way, this one's over here, and so on and so forth. Again, they're oriented randomly still. So the net result of this situation is no transverse magnetization. Does that make sense? Give a couple seconds. I see a thumbs up. I see a bit of nodding. Great, great. Okay, cool. So this is the concept of the net magnetization vector. When we have hydrogens in a magnetic field, we get a magnetic field from the body or from whatever tissue or material is in the scanner that is oriented along the magnetic field. So we know what we have to work with now. We have this magnetic field that's oriented with B0. There is one other important thing to touch on here, and that is the only equation that we are going to bring up in this whole lecture series. It is short and it is very important, so this is why we're including it. And that is the equation for the precession frequency of these atoms, right? Because they're all spinning, they're all precessing like that wobbling top. And it turns out we know what frequency they are spinning at. So let me just draw it above. Hopefully this doesn't get too crowded. Precession frequency. Okay, so that would be looking at these blue arrows, which I'll draw kind of like underneath to kind of link the two ideas together. And the equation here, it's called the Larmor equation or the Larmor frequency. I'll actually write that out for you so that we have it somewhere. I always drew it as a fancy F, so I'm going to continue doing that. F. This is equal to the gyromagnetic ratio, which is a gamma, and then that's multiplied or dot producted by the B0 field. And that's it. It's just two things multiplied together. The gyromagnetic ratio is a constant that is different for each particle that we're looking at, or each atom. For the hydrogen atom, it is like 42 point something. I will say 5. I think it's like 0.6 or something like that. Maybe I should look that up. Maybe I should have before today. But the units are megahertz per Tesla. And that is important because that means that our frequency is going to be in megahertz generally, and it varies depending on the field strength, right, per Tesla. That's why it's multiplied by, oh, thanks for looking that up. 42.58. So I was almost there. Sweet. So yeah, it's in megahertz that these hydrogen atoms are going to be rotating at 3T, which is kind of like the the typical research scanner specification these days, or field strength these days. That's near like 127 or 128 megahertz, right? That means that these things are spinning more than 100 million times or cycles per second, so very fast. This is actually a fairly large gyromagnetic ratio, which is another reason that we look at hydrogen, because changes in field strength cause differences in precession frequency, which is quite important, which we'll touch on once we get to gradients. But hopefully that makes sense. If we know the field strength that we're putting these hydrogen atoms into, we know how fast they will be precessing. That is very important. It doesn't really affect our net magnetization vector, but it'll be quite relevant later. So that is what happens when you're putting hydrogens in a magnetic field. I got a question here. I'll read it out. Why do we always talk about hydrogen in water and not in other biological molecules like sugars and fats, which also have hydrogen? Great question. I would say, well, there's a little bit of stuff we can talk about once we get into the idea of T2 times, or just basically how quickly spins dephase, or how quickly we lose signal. But if we're not at that level yet, I would say the simplest response is there is a lot more water in the body than anything else. So it's kind of our primary population of hydrogen atoms. And that's kind of like a good starting point for now. There's a lot of water in the body and a lot of hydrogens in there. It's present in other molecules and is affected in the same way once it's placed in the magnetic field. So we can kind of think of this as just what happens to hydrogen atoms as a whole, but actually considering atoms that are in different molecular situations depending on their chemical bonds, like Chelsea just touched on, or the molecules that they're components of. It does kind of change a little bit about how hydrogen atoms act, and that's just because it's surrounded by different kind of magnetic conditions. We'll touch on that a little bit later, but that's kind of a bit more of an advanced topic. We'll get there eventually, though. Any other questions about hydrogen atoms as I kind of scroll down? If so, they're very welcome. But if not, we'll move into talking about the net magnetization vector in more detail. All right, great. I actually only have a few things to touch on, as it turns out that I found it easier today to talk about it mostly in the above diagram. The only thing that I have to touch on here, I'll just draw a magnetization vector and its component spins, and then we're going to talk about phase of precession, because phase is a bit of a weird concept that is very relevant. Oh, my dark green back. Okay, so we've got our B0 field. It's big and strong. It's 3 Tesla, which tiny side note is like more than 100 times stronger than the Earth's magnetic field. And that is also, there's a reason for that, which I might ask you guys about in a second or two. And then we have our net magnetization vector, which I'm going to draw larger than it really is, just so we have more space to work with. It's just going to be labeled the NMV. We've already talked about how it is oriented upwards, or with the B0 field. We've talked about how there's no transverse component. And we've talked about how we know the precession frequency of our different hydrogen atoms, which I'll draw over here. It's a bit of a rehash, but we're getting somewhere, I promise. Okay. Now, another way to describe why there's no transverse magnetization, and something that's worth kind of touching on here as it comes up a lot later, is because these hydrogen atoms that I have on the right here are at different phases of their precession cycle. So I'm going to just draw a little mini diagram here for the concept of phase. That's below. So phase, I guess, in its most simplest form. Yeah, okay, before we move on to that, Zara was asked to explain why the net magnetization vector is oriented upwards again. That's because the name net magnetization brings us to the concept of kind of like, how does each hydrogen atom's own individual little magnetic field that I drew earlier, how do they add up? Is there kind of a surplus of magnetic fields in any specific orientation, or do they all cancel each other out like they do at rest? Now, when we have hydrogen atoms that are in the B0 field, the hydrogen atoms tend to orient upwards or downwards with the main magnetic field, and there actually are always more hydrogen atoms oriented upwards than downwards. Thanks for bringing this up, because that's a concept that I just kind of glossed over, but it is quite important. So we know that hydrogen atoms can either be oriented up or down, but there's a reason that more hydrogen atoms are always oriented upwards. And that is that, I'm just going to start writing stuff down here. So more spins oriented up, than spins oriented down. That's because each of these, why is more H oriented upward? Yeah, we're getting there. So each of these states for hydrogen atoms has a different energy level associated with it. And it turns out that when hydrogen atoms are, when they're oriented upwards with the main magnetic field, they're in a slightly lower energy state than the ones that are oriented downwards. If we think of this as kind of like, it's just basically the path of least resistance, like how, like what determines how a river flows. The particles that we're interacting with all want to just do the easiest thing possible. They're lazy or efficient, depending on your mindset on any given day. So as many hydrogen atoms as possible want to be oriented upwards just because it's slightly easier for them. But not all of the hydrogen atoms can do that, just because magnetic fields interact, right? And if two objects have the same magnetic field, like a positive pole aligned with a positive pole, they'll repel each other. So there's some interactions there that cause some of these molecules to say, fine, you win this battle, I am not going to be oriented upwards because you already are. I'll go to the next lowest energy state, which is oriented with the magnetic field, but in the opposite orientation, which is downwards. So I'll just kind of explicitly write that out so we have it in our notes when I eventually share this stuff with you. So oriented upwards is a lower energy state than oriented downwards. And that is essentially why there's a surplus of atoms that are oriented upwards. There's more nuance to it than that, but not really worth getting into for our purposes, because at this point we can kind of just jump into the net magnetization vector stuff and generally kind of hand wave the complicated quantum mechanics that are influencing individual hydrogen atoms. We don't need to go there, but we do. It's worth knowing that the energy state of atoms oriented upwards for hydrogen atoms is lower than downwards. If you want to look into this further, this is determined by field strength, and the concept that I'm referring to here is called the Zeeman distribution, I think, or no, it's the Zeeman reservoir that refers to kind of like the body of atoms that are oriented upwards. I think it's, if I remember right, it's the Boltzmann equation or Boltzmann constant that determines what the actual distribution of up versus down is. That is another equation that we just don't really need to go into right now, but if anyone wants to learn more about that, I am happy to share resources with you. We're just going to kind of gloss over it for now. As long as you understand that there's more up than down orientations, and this varies by field strength, which I can also write down here. That's all we need to know at this level. I'm just going to draw a little box around it. So now, while we're here, I'll just mention this is good, because now we know that precession frequency varies by field strength with that Larmor equation of gyromagnetic ratio dot B0, and we know that our net magnetization vector actually becomes larger in magnitude with field strength. So hopefully from those two ideas, you can kind of begin to see why having a stronger magnetic field or a higher field MRI scanner is beneficial. So say we move from like 3T to 7T, which is kind of the next typical step in scanner field strength. That makes a big difference in terms of the magnitude of net magnetization vector, because there's even more of a surplus of up atoms or up hydrogens than down hydrogens, just to kind of simplify things, which means we have more signal that we can work with later on. And our hydrogen atoms are spinning faster as well, which is generally positive. That'll come up when we're talking about gradients. Hopefully that makes sense, Sarah, and for everyone else. If there's any follow-up questions, let me know. I'm happy to dive into a little more detail or plan for some follow-up resources, depending on what people want to know about. But for now, we're going to get back to my mini phase diagram. And thanks again for the question. Now that we have a little bit less space, I'm just going to move this over. Oh, I'm supposed to be pressing this button. Aha, okay. I read back to redraw a net magnetization vector that's now smaller. Perhaps that means we've moved to a 1.5 Tesla scanner in this example, because that would give us a smaller net magnetization vector. Okay, so phase. Back here, phase is the concept of what state an object is in a cycle, right? So one example would be spinning in a circle. I have headphones in, or I could just like spin in my chair and show you the cycle of me, rotating away from the computer and back towards it. That's a cyclical motion. Or the same thing with the pen or the wobbly top as it rotates around that vertical axis. That is a spinning motion, a cyclical motion. So I'll just draw that here. Again, this is kind of like a top-down view of a hydrogen atom, and it's got some transverse orientation that's represented by that red arrow, and then it's undergoing some cyclical motion in the clockwise direction, typically, that I'm going to draw in blue here. So this hydrogen atom is spinning clockwise. It's precessing clockwise, right? Now we typically, we can talk about this kind of motion in terms of degrees, right? So if I have a couple other states here of rotation, I'll just kind of draw where it started so that we know kind of roughly what's going on. This one's going to go in the opposite direction. Okay, so I've got three different phases here or like three different phases or steps in that cycle, right? So the first one here, just to give you guys an idea, and we're going to ask you for the values of the other two. The first phase that we would say that this or this hydrogen spin is at, relevant or relative to its reference, is 90 degrees, right? Just because it's completed 1/4 of that circular motion in my diagram to the furthest left, that full cycle. It's completed basically a quarter turn. It's a quarter of the way through its rotation. We can refer to that as 90 degrees. Okay, so Can someone in the audience tell me what phase we would denote state 2 as? That's the one in the center there. Right, Chelsea says 180 degrees. That is definitely right. Thanks for that. Yeah, so now it's completed half of that motion, and out of 360, half of that is 180. This is kind of the most conventional way to talk about phase in MRI, so we're sticking with it. And then how about number 3, diagram number 3? And Eli says negative 90, totally right. You could also say, if we were considering the clockwise orientation, it'd be 270, but this was my crazy curveball that Neela got immediately. Yeah, you can also have, it's all relative to a starting point, right? So if you consider the phase backwards, you can consider it negative 90. Totally fine, that'll come up a little bit later, but that is the concept of phase. I'm glad we're all kind of snapping to that concept pretty quickly. And again, just another way to kind of contextualize the transverse components in terms of phase is that each of these hydrogen atoms that is composing our net magnetization vector has a random phase. So they all, in their precession cycle, so they're all canceling each other out and there's no transverse magnetization. But all of them are oriented vertically, so there is a net vertical orientation of the vector. Hopefully that makes sense. As from now on, we're basically talking about the net magnetization vector and not so much the spins anymore. Again, just because when you look at spins, things get quantum very fast and very technical, which is fine, but when you're learning this stuff for the first time, it's easier to think of it in terms of vectors, and then we can kind of use classical physics explanations, which work quite well for MRI if we kind of simplify it to the vector version. All right, sweet. Oh, I have an animation here, but I don't think we need to look at, well, maybe some people have not learned things with my beautiful drawings. As the last time I practiced them was for my defense, which was like, 10 months ago. So maybe not as good as they were back then. Just wait until you see me draw a brain. Practiced for months and got so far. But yeah, this animation here is just showing us kind of how we would split down an individual hydrogen atom spin into vertical and transverse components. They've got the transverse component in yellow here. Play again, please. So hopefully that makes sense for everybody. Right. And again, we can see that transverse component is rotating, whereas the vertical component is not. All right, sweet. So moving on to how we actually measure the net magnetization vector. Doing pretty decently, I'll just give everyone a heads up. I'm planning on giving everyone a break about halfway through. I hope people don't feel like this is going too slow. But again, when I was learning this stuff, I needed lots of time to absorb. So I want to make sure that everyone has a little bit of extra time and space if they need it. And when you're reviewing this, you can just watch it at 2x speed and catch up really fast. Okay, so now that we have a net magnetization vector in the scanner, we want to record it in some way, right? We want to actually manipulate it and measure it so that we can figure out how many hydrogen atoms we're actually looking at, right? Because if we know the field strength and we know the gyromagnetic ratio of hydrogen, oh, sorry, that's for the Larmor equation, but say we can actually figure out how large our net magnetization vector is, then we can get a sense of how many hydrogen atoms are contributing to it. So again, drawing our B0 arrow, which is very large and intimidating and can pull things into the scanner and whatnot, as we all know. And we have our net magnetization vector, which I'm going to draw down at the bottom here. Still definitely not to scale. Also, I've panned away. Come back. I recently discovered that this version of OneNote doesn't have scroll bars by default, and I haven't figured out how to put them back on yet, which is very inconvenient. So we're just kind of like finger scrolling for now. But here is our net magnetization vector. Key concept here. If we want to actually like measure this net magnetization vector, it's really not great to measure it right now when it's oriented with the B0 field. And we know by default that is what the vector is doing. It's oriented with B0, right? The problem here is that if we just measure, how much magnetization or the strength of the magnetic field in the body right now, the net magnetization vector is much smaller than the B0 field strength, which means you're basically, it's a fraction of the size, and you're essentially not going to be able to tell what is the net magnetization vector and what is noise. There's just interference between the two fields. And again, we've talked about kind of magnetic fields adding up. So those two vectors are going to add up, and we're basically just going to only see the main magnetic field, B0, because the NMV is so small in comparison. Even how I've drawn it here is much too large for the actual amount of magnetization that we have to work with. And the problem, even if we increase field strength to increase our NMV magnitude, it's exacerbated because then we have a larger B0 field as well. So really, we shouldn't be measuring the NMV when it's oriented with B0. And it turns out the engineers that make MRI machines are smart, so they don't do that. Instead, the goal is to draw our B0 field again and draw our net magnetization vector we want to basically tip it into some other orientation so that we can look at the transverse component instead of the vertical component of this vector. Now, like I just touched on, there is no transverse component to our NMV right now, but if somehow we use some physics to orient our NMV in this transverse direction, then suddenly we are just measuring the magnitude of the NMV if we're measuring transverse magnetization, right? So I'm just going to put a note up here. Want to record NMV in transverse orientation. Now, I've got an analogy to kind of explain this in a more intuitive fashion. Imagine that you are trying to talk to a friend at a concert or a large social gathering or something where there's a lot of background noise. You might need to, raise your voice to even be heard by the other person, or if they're just talking at a regular speaking volume, it's going to be really hard to hear them over the background noise of like the loud concert or the background hum of other conversations. And that's kind of what's happening when we're measuring the NMV with the B0 field in the background. There's a lot of background noise that's kind of just going to be overpowering the NMV's influence on our signal. But if in the same scenario, you just like in a concert, you just sent a text to your friend or some sort of like message that they could read on their phone, then the background noise is still there, but it doesn't affect your processing of the info in that message, right? Because you're just reading it. There's a whole different medium there. And that's essentially the situation when we have the NMV tipped into another orientation. The B0 field is still present, but it's not affecting our measurements because it's oriented in a different direction and doesn't really influence stuff in the transverse orientation at all. So that'd be the difference between talking to your friend at that concert versus reading a text. One is much easier to understand because it's not being interfered with by the background noise. So hopefully that makes sense. And now we need to know how to pull the net magnetization vector into the other plane in order to measure it. And like I said, we do that with tipping, also known as excitation. So I'm just debating whether to draw stuff here or the next slide. I think I'm going to move forward to the next slide, and we'll grab some stuff here, and then we'll take a break. Okay, so the last concept we're going to talk about is tipping the net magnetization vector. So we're just going to not bother drawing the B0 field for now, because it doesn't really matter to us. We're going to be ignoring it as much as possible. So I'm going to represent this as M0, which is just our net magnetization vector, just another notation for it instead of NMV. And then if we can essentially find some way oh boy, this arc was not perfect. If we can find some way to get our net magnetization to tip and get oriented along that transverse plane, then we're measuring it in the transverse plane, and we're in good shape. So this is our ideal orientation in our basic example, and that requires a 90-degree flip or 90-degree tip, typically flip in MRI. And that's called excitation. Now, the way that we do this is by applying another magnetic field called B1, which I briefly gave you guys a heads up was going to come up. And I'm going to represent it as a sine wave, fairly high frequency, B1, okay? And that magnetic field is oriented in the transverse plane. Now, back to the right-hand rule, if, again, up and down in my camera is the vertical orientation with B0, we have the net magnetization vector, which is represented by my fingers here. I'll do this way. So it's oriented vertically, and then we've got the B1 field being applied, which is my thumb. Yeah, I think, can I? Yeah, okay, great. So I've got my thumb here, which is the B1 field orientation. And now, because there's two magnetic fields, the NMV and B0 here, there's going to be a force applied, which is going to cause the main magnetic field we're concerned with, M0, to tip in the direction of my fingers, right? So now I've just got like an alligator mouth closing. So if we apply the B1 field at a right angle in the transverse plane, the NMV is going to tip towards this new, more exciting magnetic field. It's going to want to align itself with B1 as determined by the right-hand rule. And this is relevant because this is all fine and dandy, except as soon as the net magnetization vector is oriented off vertical, it's going to begin to precess, just like the hydrogen atoms that are off axis and aligned. So I'm just going to start drawing that here. So we have our original orientation of the net magnetization vector. I'm actually just going to switch this to NMV so that we're consistent across the slides. Sorry, everybody. And we have our B0 field that's oriented vertically as well. As soon as we have some tip, and this is our current orientation of our NMV red arrow, even though the B1 field over here is all enticing and exciting, and the NMV still wants to align with B1, there's now a transverse component to the NMV, which I would like to draw in green here. Thank you. Dot it. And that is going to interact with the B0 field, which again is very strong, has lots of power, and it's going to cause precession. So this NMV is immediately going to start wheeling away from the B1 field, which is not ideal, because we know that the net magnetization vector and all of its component hydrogen atoms are spinning millions of times a second, megahertz, right? So it's spinning very fast, and that means even in like the fractions of a second that are required in order for the NMV to tip down into the transverse plane, because the net magnetization vector is spinning, it's no longer going to be kind of like well oriented or lined up with the B1 field. And if we just consider what happens when the net magnetization vector reaches 180 degrees in phase. So say, I'm just going to draw in blue over here. We'll fix our arrow a little bit. So this is 180 degrees in phase. Oh, my 0 became a degree sign. And we have our B1 field still being applied in that other orientation originally. What's actually going to happen is the same force that caused our NMV to be tipped towards the B1 field in the first place is actually going to apply that force in the same direction and cause our new blue dotted line NMV to be tipped back into the vertical orientation. It's getting pulled in the same direction. So so yeah, I'm going to try this with my arm. We'll see if it helps at all. So we have our net magnetization vector. It's vertical. It gets pulled this way a little bit, and then it is rotating very fast. So it gets all the way back over here, oh boy, to the other, to the 180-degree orientation state. And that same force is just going to pull it back vertical, which means that essentially the tipping force that we want is getting canceled out like immediately, unless we use resonance. That's the R in MRI, magnetic resonance imaging. Now the concept of resonance is very fascinating. It's essentially applying a small force at a frequency that is most effective to compound the effect of that force. Classic example of resonance is when an opera singer, a soprano, I think if I'm not mistaken there, sings a very high note. It can shatter wine glasses, which I've never seen happen, but you know, it's a classic example of resonance, and that's because that note that the opera singer is singing is causing vibrations in the air at a certain frequency, and that frequency just so happens to vibrate the glass of the wine glass enough that the vibrations get bigger and bigger until they're large enough to generate a force that breaks the glass. Same kind of concept in MRI. We have a B1 field that is much smaller than the B1 field. It's not as strong, but it's applied at a frequency that matches the precession frequency of the net magnetization vector. And because of that, the field is always oriented at the kind of like at the right angle in the transverse plane to just continually tip the net magnetization vector into the transverse plane. I have a couple of resources here to help explain why this is happening. I'm going to go to the video. So this video has a great visualization of what's going on. It's a little bit more technical than we would like for this series, but this specific section hopefully will help us to understand what is going on with tipping. Hopefully it works okay over Zoom. It looks like it is on my screen, so hopefully the same for you guys. Don't really need to worry about the text so much. I think I need to go forward a little bit. All right, great. So here on the right, we're showing what exactly is happening when we apply a B1 field. Our net magnetization vector, which is in purple, is being tipped. And you can see at the bottom, it's noted as the rotating frame, which we can talk about a little bit later. I think we'll just jump into that after the break. But essentially, we're getting a slow tip because that B1 field is always oriented at a right angle to our purple arrow. Now, in reality, when we're talking about precession of the net magnetization vector and how it spins, I'm talking in the lab frame, which is on the right here. Sweet, it's getting played again. So you can see that instead of there being a misalignment of the B1 field in pink with the net magnetization vector in purple, there is always a right angle between the two that helps the net magnetization vector, oh man, it's so hard to say that so many times. Net magnetization vector be tipped effectively instead of just that tipping getting canceled out. So hopefully that helps a little bit to explain why it's important for us to apply the B1 fields at the resonant frequency of our net magnetization vector. I'm never going to get that right again. And that is why I've drawn B1 as a sine wave, just because if we're considering the B1 field as being oriented in a given direction, or like measuring it from a reference point, excuse me. If we're measuring it from a reference point, then at some points, it's going to be, that B1 field is going to be oriented towards the reference point, and at other points, when it's rotated 180 degrees, it's going to be oriented away from it. And it's just going to continue to cycle at the same frequency as the NMV and keep that angle the same so that the force applied as determined by the right-hand rule is always the same, which is going to cause effective tipping of the NMV. So if I just draw that out, then when the B1 field is at its peak in this example, and as measured by a reference point, say it's oriented towards our reference point, and then at the trough, oh no, I scrolled. At the trough, it's going to be oriented in the opposite direction away, and it's going to be cycling through those orientations at the same rate as the NMB. So if anyone ever asks you what the resonance means in magnetic resonance imaging, this is what it's referring to. It's referring to applying the B1 field at the resonant frequency of the NMB, and we know that resonant frequency of the NMB all the time because of the Larmor frequency, which I touched on before. So I'll just actually write a note here so that we have something in the slides. So what I'm going to write down is tipping requires application of B1. I'll change colors here. B1 field at the resonant or Larmor frequency. So that resonant frequency of the NMV. Does anyone have any questions about that? All right, very great. Thanks for listening so far, everybody. I am going to give us a 5-minute break, and then we'll come back and talk a little bit about gradients before we wrap up this session. So we'll stop the recording for now and start again when we get back. Okay, great. So we're recording again. I will jump back into things. Hope everybody is feeling all right about this kind of stuff. Happy to answer any follow-up emails if you're kind of letting things percolate right now and then things don't line up later, just send me an email. We can always touch on stuff as a refresher at the start of next class. So I talked about before the break how we're going to move into gradients, but I was wrong. We're going to talk about relaxation of the NMB first, because that is another important concept that I think makes more sense before gradients. So we have our net magnetization vector, and because we have applied that B1 field at the resonant frequency of the NMB, we have effectively tipped it into the transverse plane. But the next question that we all must have right now is, what do we do to record anything about this magnetic field, right? How do you actually measure a magnetic field? It's not like it's gonna, just have like a measurable light, or, it's not a physical thing you can just like feel the effects of in that kind of way. Zara's asking about the B1, the actual frequency of the B1 field. And whether you would want to set the B1 at exactly the Larmor frequency or in the range, like in the right kind of plus or minus range of the Larmor frequency. The answer there is you would want to, like if you had to pick one frequency, you would use the Larmor frequency to match it with the net magnetization vector. But in reality, the B1 field is applied in a bit of a bandwidth. So there is some effect on frequencies above and below that Larmor frequency, which is a whole other topic. It's not actually in reality one specific frequency. It's a range of frequencies that is centered on the Larmor frequency, and that allows you to also influence hydrogen atoms that are processing either slightly faster or slightly slower than the Larmor frequency, just based on their kind of local magnetic conditions, which kind of comes back again to our little chat before about how hydrogen atoms in different molecules might not be processing at precisely the Larmor frequency just because of their local magnetic environment. So yes, the B1 magnetic field is applied at kind of a bandwidth of frequencies centered on the Larmor frequency. That'll come up a little bit again when we're talking about slice selection and that kind of stuff, which is a little bit later. Thanks for that question. Okay, so to answer my own question about how we're going to measure the net magnetization vector, it's one answer is that we record it through magic. And the other more correct answer is that we measure it using a very important physical principle called Faraday's law. That essentially says, and I took these engineering courses like how long ago now? 7 or 8 years. But I would say my intuitive understanding of the law is if you have a magnetic field that is changing near a conductive material, then that magnetic field can induce an electrical current in that conducting material. So let me show you a little animation about Faraday's law that will help us to understand that these screen controls are kind of in the way here. Yeah. Help us to understand what this means for MRI. So the basic principle here of Faraday's law is there's a bar magnet on the left, and as it begins to rotate, the magnetic field is moving. There's a conductive coil of wire, probably copper or something, that's actually measuring, or it has a current induced in it that is being measured by that little green gauge on the right and recorded as a sine wave. So that actually is like an electrical current that we can record using electronics, right? So if we replace this bar magnet in this example with our net magnetization vector, we know after the vector tips, it's going to begin to precess around that B0 field, and that precession is a changing magnetic field which we can record using coils of wire, and we have tons of coils of wire in an MRI machine. These specific ones are called typically the transmit-receive coils or the send-receive coils. They are the coils in the MRI machine that both generate the B1 field in the transverse plane and then also record a current in the transverse plane as that net magnetization vector rotates around. I just want to check what our other animation is. So yeah, this is another kind of example that might help us to understand what I mean when I'm talking about the net magnetization vector precessing. So this is during excitation. If we have our B1 field, which is represented by not by nothing here, that net magnetization vector is just going to keep the same magnitude, but also spin as it's tipping, and that's it's only tipping effectively because of the application of B1 at the Larmor frequency. I'd like to get to the next tab as well, so I believe it's also useful. So what this means in MRI is as we have our NMB that's precessing, there's a coil of wire over here that will let us record a current, and that tells us essentially what the NMB is doing as it relaxes, I guess, from excitation, which is the first part of that. And then we can see the NMB is like undergoing relaxation, which we're going to be chatting about right away here. We can get useful stuff like the frequency of this wave that we're collecting that tells us essentially how fast the NMB is processing, which we know a lot about, and the amplitude of the signal that we're recording will tell us how large the net magnetization vector is, or its magnitude at any point. And that's how essentially we measure, the magnitude of the NMV and how many hydrogen atoms are contributing to it and that kind of thing. That's what determines whether we get kind of like a bright area or a dark area of tissue, although that's a little bit more advanced than what we're covering right now. So I'll just play it one more time. This is what we're actually doing when we're recording signal from the body. We're tipping the NMB and we're letting it spin around like a crazy person, and then recording the current that's induced in a coil of wire as a result of that changing magnetization field that the NMB is actually describing, right? Hopefully that makes sense. I found those animations to be quite useful when I was learning as well. Is there anything else to touch on during relaxation? Yeah, okay, we're going to go into looking at the kind of like the components of the NMB as they're regrowing. So again, we're going to kind of split the NMB into transverse and longitudinal components, or in the XY plane and the Z plane. So let me kind of set up the frames of reference that we're talking about here. So just to kind of finish this diagram here, we have the NMB, it's processing. And then we have a coil of wire, which I'm going to make green here for some reason. What a beautiful coil. And I'm going to record a signal that is represented by a sine wave that kind of gets bigger and it gets smaller. If you're wondering about that, we'll touch on it probably next session. Okay, great. So this is kind of like the general trajectory, or the general evolution of the NMB after after the B1 field is turned off and the NMB is allowed to relax. But if we look at the actual components of the vector, we get some really important information. So let's go into that. I'm going to make a little side diagram over here for frames of reference. I talked before the break about the static frame, or the lab frame, versus the rotating frame with the help of that video. So there's two ways to kind of talk about the NMB. First, we're going to have the static frame of reference. And I just want to touch on this briefly, but it is important to kind of make sure we keep track of what the visualizations I'm talking about actually mean. So if we consider just like X, Y, and Z axes, and we have a net magnetization vector that is within this frame of reference, say we've got it oriented in the transverse plane, which is this kind of like XY plane. Let me just kind of draw that up for you guys. See how good I am at drawing in 3D. Immediately poor. Awesome. Okay, so this XY plane is also known as the transverse plane. Let me put that up here. Transverse or XY plane. Hopefully that's relatively reachable. Maybe I'll improve my plane word. And in this frame, the X, Y, and Z axes are rigid, which means that if our NMV is processing, we can see it spinning essentially. So if we draw like the relaxation trajectory that we just watched in that animation, it's going to kind of look like, like it's kind of just, that doesn't really help that much, eh? I'm just going to draw a little portion of it. So it's going to be actually like spinning in our XY plane, and it's going to be like returning at kind of odd angles until it gets back to being aligned with the Z axis, which is kind of our conventional B0 orientation. So that's what's being shown back in this animation here. So I'll play just one more time. This is our static frame of reference. The NMB is the thing that is spinning. And you can see its transverse and longitudinal components there are shown in yellow and orange. And then the main vector itself is in red. So it's actually spinning, which makes the math like a little bit confusing when we're trying to figure out what MRI is actually doing. But there's another way for us to understand what is happening with the NMB, and that's with the rotating frame of reference. That's the other one we kind of want to briefly touch on. So in this case, we have, again, our X, Y, and Z axes. But instead of keeping them just kind of like static, we're going to get the X and Y axes to rotate with the NMB. So that'd be represented in this like kind of graphical example. Is just the X and Y axes are actually spinning, whereas the Z axis is static. Still always oriented in the same direction. And now we have our, the two arms of our axes that are my arms in this video, and they're kind of like moving in the same direction with the NMV. And that allows us to draw these diagrams like what we've got on the left here, where instead of precession, actually, I'll scroll back up here for a second. This diagram on the left is in the rotating frame, because this means I don't have to draw the NMV in its weird cyclical, getting lower and lower as it processes. I can just say, okay, it's oriented with the Z axis, and then because our X and Y axes are spinning, this vector is just tipping. So we don't need to, we kind of remove all the confusion of precession if we just kind of factor precession into our frame of reference. Kind of like the difference between being on the outside of a spinning carnival ride where you can see all the people inside going crazy and spinning around in circles, whereas if you're actually in the ride, then the people to the left and right of you look pretty normal, and it's the outside world that's spinning. It's just where we put our references that help us to understand what the NMV is actually doing. So that's worth kind of keeping in mind. For the most part now, we're going to be talking about stuff in the rotating frame, but it's worth remembering that the NMV is doing lots of messy precession as we're kind of going along with our diagrams. But it's much easier to draw if we simplify and kind of factor that rotation, that precession, into our frame of reference. Okay. So let's look at our longitudinal component first of what's actually happening with the NMV as it relaxes. So to save myself some drawing, I'll have to draw something for these notes so that they're kind of comprehensive when you guys have access to them. But for now, we're going to be looking at the orange component of this vector. Oh no, sorry, it's red. I misspoke last time. The red component of this arrow is our longitudinal component. That's the part of the NMV that's oriented with our Z plane. You can see that over time it is regrowing. It's getting larger as the NMV processes and returns to its original orientation, right? So that can be described by a curve. I'll just let this play one more time. So we kind of see that at first the regrowth is fairly quick, and then once it gets larger, the vector grows more slowly. All right, cool. So that can be described by this little graph that I'm going to draw here. We'll make the axes black, I guess. I'm going to call it the longitudinal regrowth chart. So if we consider the magnitude of that red arrow in the diagram, our y-axis here is going to be the percentage of original. I might give myself a bit more space here. Percentage of original NMV magnitude. Yeah, I'll write out magnitude. I'm going to give myself even more space because I wanted this to be really clear. So at rest, that NMV is going to be at 100%, right? Let's draw this in red. And let's say that on our y-axis, that's up here, 100%. And this axis down here, I'll scroll down a little bit if I can without opening the type menu. This axis over here is time, which I'll put in black. Oh no. That's going to be milliseconds. Our curve, which I'm sure you guys have probably seen before if you've learned this kind of stuff, looks like this. It's quite steep, and then it levels out and approaches that 100% mark. That looks like an exponential decay, I imagine, because it is. So there are some important characteristics of this curve. And what we care about most in MRI, or kind of like the constant that we use to describe this curve, which differs between tissues, which we'll get into next time again, I imagine, is the T1 value. Now, T1 describes the amount of time that it takes for this component of the NMV to return to 66% of its full magnitude. So let's mark this over here. This looks like about 2/3, right? Okay. That means over here, if we draw out our dotted line to where the point that is on the curve, And then we take it down to our time axis. This is T1. The amount of time in milliseconds generally that it takes for the NMB to return to 66% of its full magnitude. Okay. And that, I guess, will come up a little bit later. The other important, oh, is it 63? Fair. Yeah, my bad. Thanks for the correction. Clearly, I haven't had to talk about this in very specific detail in a little while, so my apologies. Let me correct that on the chart here. Okay, I'm just going to move this section over on our frames of reference. Give myself enough space to talk about the transverse component. Okay, so that's our longitudinal regrowth chart. And let's go back to the animation here to look at the transverse magnetization. So looking back at this NMB example, we have, after tipping, the NMB is like completely in the transverse plane, that XY plane, right? And then over time, that yellow component, which is the magnitude in the XY plane, the transverse component of the NMB, it's decreasing, right? And it turns out that happens quite quickly. And we'll get into the mechanics behind it next session as well. But you can see here that, yeah, the yellow arrow there is decreasing in magnitude. I'll flip back to my drawings here. And that can be described by a second curve, which I will label over here. This process is usually called transverse decay or transverse dephasing or transverse relaxation. I think decay is my favorite of those. Same axes though. So again, we have instead of percent of the like original NMV magnitude, we have the percent of, say, maximum, I'll keep it to max. The percentage of max transverse magnetization. Magnetization is such a long word. Okay, so immediately after the tipping is complete, we have our transverse magnetization at 100% again. I just draw that up above. So that means that this curve starts at time 0, which I will label here. It's also in milliseconds. This line starts up at the top and then very rapidly decays. So instead of going up and out, this goes down and out, if that makes sense. Now, the other constant that is all over the place in MRI is, instead of T1, T2. And thanks to Zara, I'll get the value actually correct this time. T2 refers to the amount of time that it takes for this curve, or this transverse magnetization, to reach only 37% of its maximum. So that'll be somewhere around here. If you're wondering, why did they pick 63% and 37%? I don't have the exact answer for you, but I've always thought it's probably just because the physicists who were first doing this kind of stuff found that those were very useful quantifications of these curves. Because you kind of get like a very large, or you can get differences between tissues once you allow NMVs in different conditions to evolve for a long enough amount of time. But it's worth noting that I've drawn these diagrams to make them look like T1 and T2 are quite similar, but actually they are not. T2 decay happens a lot more quickly than longitudinal regrowth. So if I put actual timescales down here on the x-axis, the return to 100%, which I'll just kind of like dot out here, say it happens like at the end of this of these axes. I'll just kind of continue the line here. Let's say this happens in, I don't know, 1200 or 1500 milliseconds. I'll put 1500 just to be kind of give myself a bit more time. This depends on the tissue that you're looking at, but usually it's over a second, right? 1,000 milliseconds is a second, so it takes a while for our longitudinal regrowth to fully complete. Whereas a T2 time, let me just grab my book here. Okay, this actually is even longer than that. All right, cool. So this amount of time that it takes for our longitudinal or the transverse decay to occur and for magnetization to completely return to zero in the transverse plane is somewhere around like, oh, I don't know, 100 milliseconds or something like that. So it's quite a bit faster than longitudinal regrowth. These are just ballpark numbers. Let me give you some actual actual values for different tissues, which again, we can kind of get into why this matters later. I'm just going to draw a box up here with some example T1, T2 times. How do I have this laid out? All right. So T1 time and T2 time. And again, these are in milliseconds. And then we're going to say we have in water, in gray matter, and in white matter in the brain. White matter tissue is a lot more fatty. That's kind of the main difference that matters for MRI. I'm going to kind of draw out this box. Okay, so in water, our T1 time is around 4,000 milliseconds. This is from a textbook that is from my favorite textbook on MRI physics. Whereas the T2 time is around 2,000 milliseconds. In gray matter, our T1 time is down to 1,800 milliseconds. So our longitudinal regrowth is happening more quickly than in water, and our T2 drops way down to 100 milliseconds. And in white matter, our T1 time drops further to 1,000 milliseconds, and our T2 drops down to 60 milliseconds. Now this has a lot of implications, but the one I want to highlight right now is that our T2 time, when we have lost 63% of our transverse magnetization, and we only have 37% remaining in white matter and in gray matter, is very fast. So that magnetization in the transverse plane, it disappears very quickly, which means that we need to measure it very quickly in order for there to be anything left to actually measure, right? So that's worth keeping in mind. And also, the sooner that you try to measure that NMV again, if you do it too quickly, then the NMV won't have fully regenerated to its maximum longitudinal magnitude, which means you might have like less signals. So you need to kind of wait a fair amount of time in between pulses or in between measurements in order to allow that that NMV to regrow or return to its longitudinal max. Okay, so that's what I've got for relaxation. These two curves are very important, and they'll come up again and again as we're talking about structural imaging, especially. And I think our next topic is gradients, which is a whole other can of worms. I don't think I'm going to be satisfied with fitting that into 17 minutes, so I think we're just going to wrap up here and leave gradients and actually, how we take this information from the NMV and turn it into an image. We're going to jump into all of that next time. So allow me to just kind of briefly recap with a few. I'm just going to skip past all these things that we didn't get to. A brief recap of the important concepts here. Debating whether to actually write them out or just talk about them. How about instead, I just kind of move through our diagrams so that we have some visuals as I'm talking through it. Covered a few key things today. in MRI, we are looking at the hydrogen atom. We're doing that because there are many hydrogens in the body, whether they're in water or other molecules. We're doing that because it has a nuclear spin of 1/2, which allows us to actually manipulate it with magnetic fields. And we're doing that because hydrogen has a large gyromagnetic ratio, which means that changes in our B0 field strength or our MRI field strength have a big effect on how hydrogen processes. That will be very relevant for gradients, which is the very next thing that we're going to cover. When you put hydrogen atoms in an MRI, instead of being randomly oriented, they tend to orient up and down with or along the B0 field orientation, which I guess I didn't mention, but is along the body of the person in the scanner. So kind of from feet to head as someone's lying down. That's the orientation of the MRI field. Now there's always more hydrogen atoms that are oriented with the B0 field than against it. That is because it is a lower energy state for hydrogen atoms or just protons, as they're sometimes called, to align with the magnetic field than against it. But they can't all be aligned with the magnetic field, so some are still aligned against the magnetic field, and this can be defined or described mathematically by this Zeeman distribution, the difference between energy states. So that's mathematically determined. Also, because these hydrogen atoms are aligned not perfectly with the B0 field, they precess around the B0 field, which is very important for us. If our hydrogen atoms were aligned perfectly with the B0 field, we actually couldn't see them at all. We couldn't interact with them. So it's pretty important for them to be aligned off axis. And as they're processing at that Larmor frequency, which we talked about, the gyromagnetic ratio times the field strength, we know how fast they're processing, and that allows us to interact with them using excitation or tipping that net magnetization vector. Also, we touched on how at rest there is the net magnetization vector is aligned with the magnetic field because of that surplus of up-aligned hydrogen atoms, but there's no transverse magnetization because the phase of our precession of each of those hydrogen atoms is still randomly oriented, so they cancel each other out. Next, we talked about how we want to record signal from the NMB in the transverse orientation, kind of just getting away from the B0 field so that we don't see that interference, and we can actually measure just the NMB, kind of isolate it, and record signal from the NMB alone using Faraday's law, which is, it says that any moving magnetic field can induce a current in a piece of wire, which is a receive coil in the MRI machine, and that's how we're actually recording a signal that we can later use to process an image, which I hope you're as excited as I am to get into next time. We also spent some time discussing how if you want to tip the NMB, you need to be very strategic about it, because if you just apply a static field, it's not going to actually effectively tip the NMB. It's just going to kind of make it wobble and then return back to straight up and down. So you need to apply the B1 field at the resonant frequency or the Larmor frequency of our hydrogen atoms, and that allows for very smooth tipping of the NMB from its vertical orientation into the transverse plane, as we saw with that animation. And lastly, we talked about how once you terminate that B1 field, the NMB undergoes relaxation, which is basically just returning from its tipped or its excited orientation back to its equilibrium aligned with the B0 field, and the evolution of that NMB happens in a mathematically describable way, such that our longitudinal regrowth occurs in, I guess, like an exponential growth pattern, with a constant T1 describing how long it takes for the magnetization to regrow to 63% of its maximum. And meanwhile, the transverse magnetization decays quite rapidly with a time constant T2 describing how long it takes for that maximum or that transverse magnetization to lose a lot of its magnitude and be at 37% of its maximum. This will all be kind of tied together into how we take this info and turn it into an image in 2 weeks at our next session. But until then, I'm happy to take any questions or provide extra resources if you want to follow up on a topic that either didn't make sense or they want to learn more about and kind of have a better understanding of. I only have one thing to leave you guys with, and that is I put together a quick little form to collect some feedback from the class. It's just like 4 questions and a little text box if you guys want to leave any feedback on how this session went, and then any thoughts about what might improve the future courses. The goal here is both to make sure that the next courses are as useful for you as possible, and also just to collect some quick little metrics that I can use in a teaching portfolio if I'm ever applying for an instructor position, as that's pretty expected these days. And with that, I will stop our recording and thank everybody for coming. I hope that you learned something today and that you're looking forward to the next session where we can continue to kind of build on these ideas.